Everyone, welcome to the video. In this one I'm going to go through some examples of drawing the geometry of molecules using VSEPR theory and the procedure. So the first example that I've got is carbon dioxide, and first thing we need to do, step one there, is draw an electron dot structure or a Lewis diagram of this, okay? And so we need to put the more electropositive in the middle and oxygens are on the outside. Carbon has 4 valence electrons, 1, 2, 3, 4. Oxygen has 6, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, we need to of course form at least a single bond between all of these, and it's a covalent bond because they're non-metals. Okay, this electron in there, this electron in there, and this electron in there. So let's redraw that. Carbon, single bond oxygen, single bond oxygen. Carbon's still got 2 electrons left over. Oxygens each have 5 around there that are non-bonding, keeping those pairs together. Okay, we can see there's still some unbonded electrons, especially top and bottom of carbon. And if we consider the bonds around the carbon, we've got 2 bonds, each carrying 2 electrons. So that's 2 electrons, 4 electrons, 5, 6. It hasn't got its full octet. More bonding is going to occur. That electron in there, that electron in there to form a double bond. That electron in there, that electron in there to form a double bond. Notice I kept the pairs together. Okay, redrawing this. Carbon, double bond oxygen, double bond oxygen. Each oxygen has 2 lone pairs left around the outside. Okay, and we've got 2 double bonds. So there's our Lewis dot structure of carbon dioxide, which is step 1. Step 2 is we need to determine how many bonding groups are around this molecule. Okay, around this molecule, around the central atom, which is carbon. So we've got that double bond and that double bond. So any bonds or lone pairs count as bonding groups. So we've got 2 bonding groups. So its basis for the molecule is a linear basis. We're saying 2 bonding groups pushing away around a sphere will be 180 degrees apart. The linear molecule basis. Okay, step 3 is we need to determine how many non-bonding electron pairs around the carbon. There's 0 electron pairs non-bonding. So we don't need to reconsider the shape for number 4. Number 4, bonding groups versus the number of non-bonding electron pairs. It's 2 bonding groups, but all of them are bonding. There's 2 actual bonds around there. So the actual shape is back to the Lewis structure there. Let me redraw it. Carbon, double bond, oxygen. Oxygen has 2 lone pairs. So the only bonding groups are 2 actual bonds. So the shape is linear and it's 180 degrees apart. Okay. Linear molecule. Alright, let's consider example number 2. We've got nitrate. The formula for nitrate, hopefully you're starting to remember it. NO3-. It's a polyatomic anion. Okay, let's start doing our structure. Oh, I'm going to put NO. Nitrogen's the most electropositive, put it in the middle. Nitrogen has 5 valence electrons, 1, 2, 3, 4, 5. Oxygen has 6, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. Now, the charge on this ion says that there must be one more extra electron in there. And we'll come to see why. I'm going to leave it out for the moment, but maybe from next time we should put it in the beginning, and we're going to see what problems we get without putting it in. Okay, or I want red. I want to start to form covalent single bonds between the nitrogens and oxygens. So one each electron to form a new bond. Okay, redraw what we get. Nitrogen, oxygen, oxygen, oxygen. The nitrogen still has a lone pair at the top. Each oxygen has two lone pairs but a single unpaired electron. Oh, nature doesn't like that unpaired electron. You should be identifying that now. So nitrogen has 2, 4, 6, 8 electrons. It's happy, but each oxygen has 2, 4, 6, 7 electrons. Okay, so let's start doing some more bonding. This electron, oh, I don't want that. This electron and this electron are now going to form a bond. Let's see what we get. That's a terrible arrow. There's our double bonded. There's now one, oh, I don't want that line. There's now one electron there, two electron pairs there, and these ones have 5 around them. Okay. Now, what can happen is this electron and this electron could go in there to bond and form a double bond there. But the trouble is that nitrogen will have 2, 4, 6, 8, 10 electrons. So that can't happen. Let's undo that. What can happen though is this electron over here can jump over to there and now make it a bit more stable. So let's draw it again. Start counting our electrons after as well. Oh, that's not a hydrogen, that's an oxygen. Okay, now this oxygen has the 3 lone pairs. Okay, let's count our electrons. Nitrogen has 1, 2, 3, 4 bonds, so it has its 8 electrons. This oxygen here has 2 bonds and 2 lone pairs, so that's its 8. This one over here has 1 bond and 6 lone pairs, 6 electrons in 3 lone pairs, so that's 8 electrons. And this one down here has 7 electrons. Notice there can't be any more sharing, and we seem to be we're down 1 electron, and that's where this one comes in, the minus there. That is why nitrate is charged. Okay, this electron jumps in there, and so the stable form of nitrate needs to be a single minus. We need 1 extra electron. Let me redraw nitrate as it truly is using this model. Okay, this one, oh, this one had 3 lone pairs. This one had 3 lone pairs. And this one has 2 lone pairs. And there's no lone pair on the nitrogen. We put big brackets, square brackets around it to say overall it's got a single negative charge. That's how we do a Lewis dot structure for nitrate. Running out of room here for number 2, but that's okay. A little bit of room down here. Number 2, determine how many bonding groups we've got around the central atom. Central atom is nitrogen, and we've got 1, 2, 3 bonding groups, no lone pairs, and 3 types of bond, three different bonds there. So there's 3 bonding groups. Okay. Number 3 asks us to determine, have we got any non-bonding groups around the central atom? No, there's 3 bonding groups and no lone pairs. So there's only 3 actual bonds around nitrogen. So step 4, 3 actual bonds around a central atom is going to give us a trigonal planar molecule. Each of those, I'll go back, I might change to a different colour, will be 120 degrees away from each other. So we've got a trigonal planar molecule, 3 bonding regions and 3 actual bonds around that central nitrogen. I should actually have a charge on that, shouldn't I? Make it nice and obvious that we've got a polyatomic ion there. So the shape of nitrate is trigonal planar. I should write that down, shouldn't I? Okay, that was a bit of a difficult one. Let's see how ozone goes. Ozone, if you don't know, is O3. So we're going to need 3 oxygens. 1, 2, 3. Let's start with the Lewis dot diagram. Let's put on our 6 valence electrons for each oxygen. 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. They're all non-metals. They're going to share electrons. Let's share 1 each and make a single covalent bond between each oxygen there. Oh, I'll draw an arrow. Oh, I don't want dark blue, I want black. Okay. Oxygen, oxygen, oxygen. We've got 2 lone pairs and 5 electrons there and 5 electrons here. Okay, let's do some electron counting. Around this central one we've got 2, 4, 6, 8. It's good. But these outer ones, 2, 4, 6, 7, that's not good. They need their full octet. So we're going to share some electrons. Okay, let's bring that electron in there and that electron in there and see what we get. Okay, so we're forming a double bond, keeping this a single bond. So we get 2 lone pairs, 2 and a single one over there, and that one has the 5 left over. Okay, let's do some counting. Let's do it in blue. This one here, 2, 4, 6, 8. This middle one, 2, 4, 6, 8, 9. Ugh, that's not good. 2, 4, 6, 7. There's some hinting there. 9 and 7. We need to share and push an electron around. So this electron that's by itself, you should recognize that as not being good. This one, oh, I don't want to do that. This one here can join up there. Move on over because there's 9 there and 7 there. So what we now get, let's redraw. Oxygen, double bond, 2 lone pairs, a lone pair up top, a single bond to an oxygen that has 3 lone pairs. Okay, let's do some counting. Okay, 2, 4, 6, 8 for that one. 2, 4, 6, 8 for that one in the middle, and on the end, 1, one single bond with 2 and 3 lone pairs, 8 electrons. We're nice and stable. So, oh, just deleted. I want to change the size. Yeah, I just want to delete these guys. Oh, I'm deleting all of them. Let me redraw them in. I was just missing those two. Okay, so there's our number 1, our electron dot structure for ozone. Number 2, we need to go to our central atom, our central oxygen. How many bonding regions? 1, 2 bonds, and a lone pair. So that's 3 bonding regions or groups. So basis must be trigonal planar. So trigonal planar, because all those electrons are trying to push each other apart in 3 different ways. So it's 120 degrees between each bonding group. But number 3 here, one of these is a non-bonding pair. So, sometimes written like that, that bond isn't actually there at the top. So what we're actually getting is 1 oxygen, 2 oxygens, and the lone pair up top. No actual bond up top here. So instead, it's a bent molecule at 120 degrees. It's bent because its basis is trigonal planar, but it's only actually got 2 bonds. Okay, those electron pairs up the top are still pushing away those bonds. And those bonds are still pushing away at each other too. Okay, so that's why it's a bent molecule at 120 degrees for ozone. Methane. Carbon and 4 hydrogens. Let's draw electron dot diagram or electron. I'm losing my words. Okay, carbon. Hydrogen, 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 hydrogen. 1, 2, 3, 4. Valency of 4. Hydrogen valency of 1. Okay, we need a covalent bond between each electron. Is going to jump and share, and we're going to form 4 bonds here, 4 single covalent bonds. And then we're going to do some accounting and make sure that we've got our octet, or for hydrogen, it just needs its 2 s orbital ones. Okay, no lone pairs. Carbon has the 4 double bonds, so it's got its 8 electrons. It's good. Hydrogen, each hydrogen just shares its 2 covalent electrons, and that's all it needs. It's happy too. So the Lewis dot structure of methane, I'm just going to redraw it because why not? Nice and simple. 4 single bonds to each hydrogen. Okay, step 2. The central atom is carbon. How many bonding groups? 1, 2, 3, 4 actual bonds. 4 bonding groups. So its basis is tetrahedral. 4 groups equally pushing away from each other around a central atom. In 360 degrees, they're going to be 109.5 degrees away from each other. Okay, how many actual bonds? Well, there's 4 actual bonds. There's no lone bonding pairs. The actual molecular shape we just call tetrahedral. Okay, I haven't shown you this, but with these shapes, there's a way to draw them to show that they're 3-dimensional. We haven't got a planar molecule anymore. So if I'm trying to draw it in a plane, I've got to show some kind of 3-dimensionality here. And what I do is I used dashed and wedged covalent bonds. Wedge means coming out of the page. Dashed means going in to the page. And that's how we show three-dimensionality. These two here will be in the plane of the page, so they're okay. So methane is a tetrahedral molecule. Let's try ammonia. NH3 is the formula for ammonia. It's one of the ones that you're going to have to remember. Nitrogen has 5 valence electrons. Hydrogen has 1. Let's put a single covalent bond in between each and see what we get. I'm going to redraw it. Hydrogen. And we've got these two left over. Each hydrogen has its 2 electrons in that single bond, and nitrogen has 3 bonds, 6 electrons, and then the 2 lone pairs, so it's got its 8. So the electron dot diagram for ammonia is just there. Okay, the central atom is nitrogen. How many bonding regions? 1, 2, 3, 4. So it's going to be a basis of tetrahedral. Okay, but step 3, 1 non-bonding lone pair of electrons. Okay, so its basis is tetrahedral, but it's actually missing one of those bonds. So what we're going to get, I'll just go back one step, is this shape here, where this is not an actual bond up the top. And that shape is trigonal, because the base is a triangle, pyramidal, if I can spell it. So it's a tetrahedral basis, but it's missing one bond, so it's a trigonal pyramidal shape for ammonia. So it's like a little tripod. Okay, next example is water. Hopefully you know the formula for that one. Oxygen in the middle, hydrogens on the outside. Notice I'm doing it the quick way. Each hydrogen has 1 bond there, and that's enough to fill its valence shell. Oxygen has 2, 4 in the bonds, 6, 8 on the outside. Okay, so a single bond between each one. How many bonding regions do we have around the central atom? 1, 2, 3, 4. Count the lone pairs. So it's a tetrahedral basis as well. But we have 2 non-bonding pairs. What happens then? Okay, so we've got our oxygen, got our hydrogen, we've got a lone pair coming out this way. You could draw it like this, and a lone pair going into the page, but without those bonds we've actually just got a nice molecule in this plane, hydrogen, hydrogen, and 109.5 degrees between the two. What we call this is a bent molecule. We've seen that before, but it's 109.5 degrees. We saw this, another bent molecule, back when we had a trigonal planar basis that had 1 lone pair. We got a bent molecule at 120 degrees. This time we have a tetrahedral basis, but with 2 lone pairs, and we get a bent molecule at 109.5 degrees. So even though you get 2 types of bent molecules, you can distinguish them too by the angle between them. The tetrahedral one will have the smaller angle, and the the trigonal planar basis will have the larger angle, 120 degrees. All right, thanks for listening. We'll leave it there. Hopefully that video helped.